Welcome to this explainer. Today, we're diving into the absolute bedrock of modern science, what physical quantities actually are, and why standardized measurement is absolutely crucial to understanding our reality. If you've ever wondered how scientists manage to agree on the rules of the universe, well, you're in the right place.
Here's our roadmap for today. The physical world, what can we measure, base and derived quantities, and finally, the need for standards. Let's get right into it.
Section 1. The physical world. Since the literal dawn of time, humans have looked at the sun, the oceans, and the stars with just this immense curiosity. And that curiosity drives what we call science, the observation and experimentation we use to decode the reality of our world. But to actually get reliable results from all those fascinating experiments, scientists rely on one absolutely essential thing: making accurate measurements.
Moving on to Section 2. What can we measure?
There's a pretty stark line drawn in the sand here between what physics can actually quantify and what it can't. On the physical side, things like mass or time, we can measure them. We use instruments like rulers or clocks, and they have distinct numerical values and units. But then on the non-physical side, like anger or sadness, we obviously don't use instruments, and there's no mathematical unit to define them.
Let's just think about those non-physical concepts for a second. Love, fear, wisdom, beauty. These are completely vital to being human, right? They dictate our behavior and social interactions. But because they rely entirely on human perception or survey techniques, they can't be measured with physical tools. So they fall entirely outside the realm of physics.
So the major takeaway here is that physics stays strictly in its lane. Its foundation rests entirely upon physical quantities. Physics focuses exclusively on things we can measure, whether directly or indirectly. And it's through those measurable physical quantities that all the laws of the universe are expressed.
All right, Section 3, Base and Derived Quantities. When we interact with the material world, objects expose measurable features like length, mass, and time. And scientists did something really clever here. They arbitrarily selected a few of these to be the absolute foundational building blocks, kind of like Lego bricks. We call those base quantities. Every single other measurable feature is just a combination of those blocks, which we call derived quantities. Let's make this super concrete with an example. Speed is a derived quantity. Why? Well, you can't just measure speed in a vacuum without referencing other concepts. Speed depends entirely on distance and time. Since distance, or length, and time are our foundational base blocks, speed is simply derived by combining them together.
Same deal with density. The density of a material is derived. It's described in terms of mass and volume. Mass is a base quantity, and volume itself is derived from length. So you can see how literally everything in physics is systematically built right on top of those foundational blocks.
But to actually find that speed or that density, we've got to measure it. And what does that mean in practice? A measurement is basically just a process of comparison. You take an unknown quantity and you compare it against a known, widely accepted standard.
Which brings us to Section 4. The need for standards.
This highlights a massive historical problem. What happens when you don't actually have a widely accepted standard? Imagine a teacher asks 5 students to measure the length of a whiteboard using just their hands. One gets 15 hands, another gets 12. Are those measurements the same? No way. You instantly realize it's total chaos because their hands are all different sizes.
And believe it or not, this was reality. In the early days, people actually used body parts to measure length: hands, arms, feet, steps. But since my arm is definitely not the exact same size as your arm, it resulted in massive confusion. Everyone's measurements were constantly conflicting.
As the source points out, not very far in the past, every country in the world had its own units of measurements. Just think about how terrible it would be to trade scientific data or do international business if the merchant you're buying from happens to have much shorter arms than you. You'd be paying for what you think is 10 arms of fabric and getting significantly less.
The brilliant solution to this global headache was the creation of standardized units. A unit is simply a benchmark, a standard of measurement, ensuring that any person, anywhere on Earth, measuring an object will get the exact same result.
And that establishes an absolute golden rule in physics. A measurement consists of 2 parts, a number and a unit. If I tell you a board is 15 long, that is literally nonsense. 15 what? Hands? Centimeters? Miles? A measurement without a unit is completely meaningless.
Eventually, we all got on the same page. The world agreed to global benchmarks, like the International Prototype Kilogram.
This was a real game changer. It replaced subjective human body parts with objective scientific truth. And that allowed all countries to efficiently trade, grow their economies, and seamlessly share vital scientific breakthroughs. So, as we wrap up this explainer, I want to leave you with this thought to chew on. If modern physics and our entire global economy required the invention of standardized units just to get off the ground and eliminate confusion, what wild new phenomena might we discover when we invent even more precise standards of measurement in the future? Thanks for exploring the foundations of physics with me, and keep questioning the physical world around you.